April 1943. A Japanese bomber approaches the USS Helena at 180 meters per second, maintaining an altitude of 1,200 meters off Guadalcanal. The ship's 5-inch gun mounts track the aircraft, their fire control radar feeding targeting data to the gun crews below. A loader rams a shell into the breach. The projectile weighs 24 kilograms and appears identical to standard high-explosive rounds except for a distinctive nose fuse assembly. The gun fires. The shell leaves the barrel at 790 meters per second. 14 seconds later, it detonates 3 meters from the bomber's fuselage without making contact. The explosion sends hundreds of steel fragments through the aircraft's wing and engine. The bomber enters an uncontrolled spiral and crashes into the sea. The gun crew never sees the impact. They are already loading the next round. The fuse that detonated the shell contained a miniature radio transmitter, receiver, vacuum tubes, and battery, all designed to survive 20,000 times the force of gravity during firing and detonate precisely when the shell passed closest to its target. It was called the VT fuse, and between 1943 and 1945, it increased the effectiveness of anti-aircraft fire by a factor of 5. The United States Navy entered World War II with an anti-aircraft problem that was mathematical and physical. Shooting down high-speed aircraft required shells to detonate at the precise moment they passed closest to the target. Time delay fuses, set manually before firing based on estimated target altitude and speed, detonate at predetermined intervals after leaving the gun. If the estimate was wrong by even half a second, the shell exploded uselessly in empty air. Hit probability for a single 5-inch shell with a time fuse against a maneuvering aircraft at 3,000 meters range was approximately 0.5%. Destroying a single bomber required a statistical expenditure of 2,000 rounds. Contact fuses required direct hits, which were even less probable. What naval anti-aircraft defenses needed was a fuse that could detect the target's proximity automatically and detonate at the optimal distance without requiring perfect aim or perfect timing calculations. The specification demanded a device that could sense a nearby aircraft, that could function reliably after experiencing launch acceleration of over 20,000 g-forces, that could survive the centrifugal forces of shell rotation at 500 revolutions per second, and that could be mass-produced in quantities of millions. The problem seemed insoluble given the technology available in 1940. Development began in 1940 at the National Defense Research Committee under physicist Merle Tuve at the Carnegie Institution in Washington. The team included engineers from Western Electric, General Electric, and various university laboratories. They approached the problem by eliminating impossible solutions first. Mechanical proximity sensors could not survive the launch forces. Optical sensors could not function through gun smoke and could not distinguish targets from clouds. Acoustic sensors were useless at supersonic shell velocities. The only viable approach was radio. The concept was straightforward. The shell would contain a miniature radio transmitter broadcasting continuously. When the shell approached a large metal object, like an aircraft, the radio waves would reflect. A receiver in the shell would detect these reflections, and when the signal strength indicated the target was within lethal radius, typically 20 to 30 meters, an electrical circuit would fire the detonator. The engineering challenges were extraordinary. The device had to fit inside a standard artillery shell nose fuse, occupying a cylinder approximately 75 millimeters in diameter and 130 millimeters long. It required a radio transmitter operating at approximately 180 megahertz, a receiver, amplification circuits using vacuum tubes, a power source, arming mechanisms, and the explosive detonator itself. All components had to survive not only launch forces, but also the harsh environment inside a spinning projectile, traveling at supersonic speeds through varying atmospheric conditions. Vacuum tubes, fragile glass devices that broke if dropped on a table, had to be redesigned to survive forces that would crush most materials. The solution involved new tube designs with rigid internal structures, new glass formulations, and innovative mounting methods. The transmitter antenna was a wire embedded in the nose cone's plastic cap. The battery used a reserve electrolyte design that only activated after launch, preventing degradation during storage. The operating sequence was mechanically and electrically complex, but occurred automatically within milliseconds. On firing, the massive acceleration triggered a setback mechanism that armed the fuse after the shell cleared the gun barrel, preventing premature detonation. Shell rotation powered a small generator that supplemented the battery. The transmitter began broadcasting immediately, sending out radio pulses at 180 MHz. The receiver monitored for reflections. As the shell approached a target, reflected signal strength increased. When the received signal crossed a threshold corresponding to approximately 20 meters distance, a thyrotron tube in the firing circuit discharged, sending current through the detonator. The main explosive charge detonated, fragmenting the shell casing. The entire sequence from detection to detonation required approximately 50 microseconds. At typical shell velocities, this meant detonation occurred at the optimal distance for maximum fragment density at the target. Testing began in 1941 at the Naval Proving Ground in Dahlgren, Virginia, and at remote facilities where radio silence could be maintained. Early tests were discouraging. Tubes shattered, circuits failed, detonations occurred randomly or not at all. Gradual refinement of each component eventually produced a design that functioned reliably. By mid-1942, production fuses were undergoing live fire testing against drone aircraft. Success rates improved dramatically. Shells with VT fuses destroyed targets that would have required dozens of conventional rounds. Security was absolute. The fuse was classified at the highest level. Production facilities were isolated. Workers assembled components without understanding the device's function. The designation VT was deliberately misleading, suggesting variable time, when the actual mechanism was radio proximity. Operational deployment began in January 1943 in the Pacific Theater. The first combat use occurred during a Japanese air raid on Guadalcanal. Cruisers and destroyers equipped with VT-fused ammunition engaged incoming bombers at ranges where time-fused shells had been largely ineffective. Hit rates increased immediately. Japanese aircraft that would have survived conventional fire were destroyed or damaged severely enough to abort attacks. The psychological impact on Japanese air crews was substantial. Anti-aircraft fire that had been dangerous but survivable became lethal. Formation bombing attacks, where aircraft accepted casualties to saturate defenses, became unsustainable. Japanese tactics shifted toward low-level approaches and night attacks, both less effective delivery methods. The technology spread rapidly across the Pacific Fleet. By mid-1943, nearly all major combatants carried VT ammunition for their 5-inch guns. Production reached millions of fuses monthly. Each fuse cost approximately $18, compared to approximately $50 for a conventional time fuse, but the cost was justified by effectiveness. Statistical analysis showed that VT-fused shells achieved hit or damaging near-miss rates approximately 4 times higher than time-fused shells and 10 times higher than contact-fused shells. The kamikaze threat in 1944 and 1945 made this increased effectiveness critical. Suicide aircraft required destruction at maximum range. VT fuses provided the only reliable means of achieving this consistently. Comparison with equivalent weapons from other nations reveals that no such equivalent existed. German anti-aircraft relied on time-fused shells and radar-directed fire control, but had no proximity fuse development that reached operational status. British research into proximity fuses existed, but lagged American efforts by approximately 2 years and never achieved the same level of miniaturization or reliability. Japanese anti-aircraft technology used time fuses exclusively throughout the war. Soviet anti-aircraft systems were similarly limited. The United States achieved a monopoly on functional proximity fuse technology that persisted through 1945. Captured German documents show awareness of American proximity fuses by 1944, but German attempts at duplication failed due to inadequate miniaturization technology and the increasing impossibility of precision manufacturing as Allied bombing degraded industrial capacity. Limitations existed despite the weapon's effectiveness. The VT fuse required radio silence near friendly aircraft, as it could not distinguish friend from foe. Early in deployment, several instances occurred of VT-fused shells detonating near friendly aircraft, though casualties were minimal. Doctrine evolved to restrict VT ammunition use to sectors without friendly air traffic or above specified altitudes where friendly aircraft would not operate. The fuse was ineffective against ground targets because radio reflections from terrain caused premature detonation. This limitation prevented deployment on the European front until late 1944, as concern existed that ground combat would allow German forces to capture intact fuses and reverse engineer the technology. The Battle of the Bulge in December 1944 saw the first large-scale use of VT fuses against ground targets, where airburst detonations above German troop concentrations proved devastatingly effective. The radio proximity fuse represented the convergence of multiple technologies, none of which individually appeared revolutionary, but which combined to create capabilities that transformed anti-aircraft warfare. Miniature vacuum tubes, compact batteries, reliable detonators, and radio circuit design all existed separately before 1940. Integrating them into a package that survived artillery launch forces required engineering refinement rather than fundamental scientific breakthroughs. This made the achievement more remarkable rather than less. The fuse succeeded not through theoretical innovation, but through practical problem-solving, incremental testing, and manufacturing discipline. Production statistics illustrate the scale of deployment. By August 1945, approximately 22 million VT fuses had been manufactured. Peak production in early 1945 exceeded 1 million units monthly. Multiple manufacturers participated, including Western Electric, Eastman Kodak, and Crosley. Quality control was intensive, with each fuse subjected to multiple tests before acceptance. Rejection rates were approximately 3%, considered excellent given the device's complexity. Post-war analysis suggested VT fuses prevented thousands of Allied casualties by reducing successful Japanese air attacks and by shortening engagements that would otherwise have required prolonged conventional fire. The Japanese bomber approaching the USS Helena in April 1943 never saw the shell that destroyed it. The pilot never knew that the anti-aircraft fire tracking his aircraft used a technology his nation could not duplicate. The VT fuse remained classified until after Japan's surrender, when its existence was finally disclosed publicly. The miniature radio device that fit inside an artillery shell and survived forces that would destroy most machinery became the foundation for guided munitions development that continued through the rest of the 20th century. Every modern proximity-fused weapon traces its lineage directly to the device developed in 1940 by engineers who solved an impossible problem by refusing to accept that it was impossible.